Okay, so here we are in the last video for Unit 3 of AP Physics C, the Work, Energy, and Power Unit. And in this video, we're going to look at potential energy diagrams. Okay, so one thing is that a good deal of useful information about the behavior of the system can be found by interpreting a graph of its potential energy as a function of position. So U of X versus X. Okay, we call this diagram a potential energy diagram. Okay, and so that's why it's U of X versus X. Now, from this, so before we actually jump into talking about equilibrium, so you can look at the two pictures here. These are two basic ones. So the first one, as you can see, is energy versus the height above the ground. And so instead of it being X, it's going to be Y. Because it's falling. So basically we're plotting MGH versus H, okay? And so things that you can see, you could do this as a kinetic energy versus, H diagram or speed diagram, okay? But you could see that key points. Remember, the energy, the mechanical energy is never changing, so it's a constant. So that line represents the constant value, meaning that the energy can't go above that line. I know the graph goes past it, but you'll see down here, right, we've got 0 and Y max. Okay, and then you could the equation UY equals MGY, and then what happens is if the line represents U, right, that means so if the graph is what I should say represents the potential energy, anything above that would represent the kinetic energy. And so you can see at point A, right, it has a potential energy of UA, but it has a kinetic energy of what's there, right? And we would use, say K equals that total minus UA. So that's how we would find the kinetic energy. So at this point, right, it would have, let's say this is point B, right? It would have UB, but you can see above it, this would be KB. Okay, now that's for an object falling. Now, if you look at the other picture here, it talks about a glider on a spring. So it's going back and forth, right? It's on an air track. And you can see the extremes are your turning points. Okay, down here, and we'll talk about equilibrium here in a second, but there's an equilibrium point. But again, you can see the total would be your K plus U. Your energy is constant at that line connecting the two turning points. So at the turning points, this is when it's all potential. So potential is at a max and your K is equal to 0. The equilibrium point is when K is at a max and your potential energy is 0. Okay, well, how can we find the potential energy at that point? Well, you can take the derivative if you know the function, right? You could take that and take the derivative, right, and find when it's equal to 0. That's going to give you, the time it happens, the position it happens, and so forth. Okay, so let's talk about this equilibrium point. So a particle is equilibrium if the net force acting on it is 0, right, which means there's no potential energy. Okay, and so remember that force is equal to negative du dx, and at the equilibrium, it's when that's equal to 0, right? And so if I'm given a function for that potential energy, I can find the force by doing the negative derivative and setting equal to 0. That gives me my points of equilibrium, okay? And there's 3 types of equilibrium. There's stable equilibrium, there's unstable equilibrium, and there's neutral equilibrium. And stable equilibrium is when you're plugging into your test point, right, when these are equal to 0, and it's when it's at a minimum. Unstable equilibrium is when it's at a maximum, and neutral equilibrium is when it's at an inflection point. And so what does that mean? To find equilibrium, you just take the second derivative and then plug in that point, and that'll give you what type of equilibrium it is, okay? And so for stable equilibrium, we would say that the second derivative of potential, right, is going to be at a minimum, so it's going to be less than 0. When it's unstable equilibrium, it's going to be at a maximum, when it's greater than 0. And then neutral equilibrium, if that second derivative is equal to 0. So those are your 3 conditions for your equilibrium positions. Okay, so let's look at an example. So basically your steps would be, right, take the derivative, find the zeros, and then find the second derivative and plug in those 0 points into it and figure out if it's a min or a max, and that'll tell you the type of equilibrium. Okay, so here is an example. It says the potential energy function of a system is given particles of a particle is given by u of x is equal to negative x cubed plus 2x squared plus 3x, where x is the position of one particle in the system. Determine the force on the particle as a function of x. For what values of x is the force equal to 0, and then plot ux versus x and fx versus x, and indicate points of stable and unstable equilibrium. Okay, so part A is we're going to find force, right, with respect to x. So what we're going to do is say we're going to take the negative derivative, okay, of that function. And so I'm going to say negative d dx of negative x cubed plus 2x squared plus 3x. Okay, I could bring that negative sign in and say d dx of x cubed minus 2x squared minus 3x is what I'm taking the derivative of. So my force as a function of x is going to be 3x squared minus 4x minus 3. So that's my part A. My part B says to what values of this is this force equal to 0? So I'm going to say f of x is equal to 3x squared minus 4x minus 3 equals 0. This is what we're finding where our function is in equilibrium. We don't know what type of equilibrium it is in yet, but we know it's equilibrium. Okay, and so what we could do, right, is we will use good old, not Pythagorean theorem, but the quadratic equation. So negative b plus or minus the square root of b squared minus, a minus, not a plus sign, minus 4 times a times c, all divided by 2a. Okay, and again, you're going to get 2 answers. You can answer negative 0.5352 and 1.869. Okay, and so what that means, at those positions, my function has a derivative of 0. It's a flat line, or it's, a cusp of some sort. Okay, now part C says to graph them, right? And we'll just do a little sketch. So if this is my one function, or my one point, that's my other point, my f of x would look like this, right? And my u of x, so this would be f of x, right? And this is my u of x, right? And that's going to look something like, and this is just a sketch. You can do it this exactly, right? But these would be my points, right, of where I have equilibrium happening. So are those going to be stable versus unstable? Well, we can take the easy way to do it is to take the second derivative. So the second derivative would be 6x minus 4, right? And then we're going to plug in these two values and find out if it's greater than 0, less than 0, equal to 0. All right, so I'm going to say 6 times negative 0.5352 minus 4. And that, you could tell, is going to be less than 0. So this is going to be a minimum. So that's stable equilibrium. And I'm going to do 6 times 1.869 minus 4, which will obviously be greater than 0, which is a maximum. So this is unstable equilibrium. Okay, and you can tell here, right, max, min. So max is when it's unstable, min is when it is stable equilibrium. Okay, Again, my graphs aren't exactly perfect, but those are just the general ideas of what they'll look like. So this wraps up Unit 3 here in work, energy, and power. Again, this was very heavy calculus based as compared to what you would see in a Physics 1 course. So good luck on this portion of the exam. I know you guys will do great.